What's up, bitches? Today we're going to learn air-water vapor mixtures, okay? Before I start the problems, you have to know a few equations, okay? You have to understand what specific humidity is, relative humidity, and for some problems, you have to know what the dew point temperature is, okay? Specific humidity basically says the amount of water present per kilogram of air, okay? It's equal to the mass of vapor divided by the mass of atmosphere. It basically says the kilogram of water per the kilogram of air. That's it. Super simple. Specific humidity is basically equal to the vapor pressure divided by the saturated vapor pressure. This basically says that in a certain atmosphere, okay, you're going to have some air and you're going to have some water, okay? But at a certain temperature, the atmosphere can contain a maximum amount of water. The relative humidity, phi, says what percentage of that maximum water it's containing. That's it. Dew point temperature, lastly, is the saturated temperature of the vapor pressure. Okay. If your water temperature is below the dew point temperature, then fog occurs, like condensation happens. One last thing that you could know is that the total pressure in an atmosphere is equal to the dry air pressure plus the vapor pressure. I don't know if it's useful for some problems, but there's also that. And that's it. Okay, the next thing you have to know is a psychometric chart, okay? So this low-key looks like a little clusterfuck, but just take this blank psychometric chart, okay? At the bottom is your temperature. Even though it's written dry bulb temperature, just ignore that. That's basically the temperature of the air, okay? These curved lines is the relative humidity, your phi, okay? Next, on the diagonal side is your enthalpy, H. Next, on the right side, usually you're going to have written your specific humidity, okay? Just pay attention to the what do you call it, the units, okay? Because some psychometric charts, I've seen that they write grams per kilograms of dry air, okay? So just pay attention to that. Also, these weird diagonal lines, that's your specific volume. And that's it. When you put it all together, you get this wonderful psychometric chart. For some problems, you also need to take into consideration the dew point temperature, which are these lines over here, okay? But probably you won't need to use those unless it's like a very specific problem, okay? So what you have to understand with this chart is that for most of your problems, you need to pay attention of the temperature, relative humidity, specific humidity, enthalpy, and sometimes specific volume. And for some rare questions, you need the dew point temperature and the wet bulb temperature. Okay, the wet bulb temperature is this weird line over here. It's whatever is parallel, but that's like a very unique question, okay? Anyways, what I'm saying is basically you have 1, 2, 3, 4, 5, 6, 7 values possible. If you have any of those two with the psychometric chart, you could find all of them, okay? So for a lot of questions, you're just going to find these two. And with these two, you can find everything else, for example, okay? And that's it. That's your psychometric chart. So this is what your problems are going to look like. You have stage 1 over here, T1, phi 1, T2, phi 2. This is a simple heating problem, okay? So you have Q that comes out. The first rule for this problem is that the omega stays the same, and that the second rule for this type of problem is that Q is equal to the mass flow rate of dry air times the difference in enthalpy. That's it. For this type of problem, you have to consider 3 stages, okay? Over here, it's stage 1, so you have like T1, phi 1, omega 1. Then, once it goes through the heating section, it's the second section, okay? Since water does not change, omega 1 is equal to omega 2. Here, water is introduced, so omega 3 is different from omega 2. Okay, that's your first rule. The second rule is you have to understand that E in equals to E out. Okay, going from stage 2 to stage 3. What that means is that the air that's entering, the energy from the air plus the energy of the water is equal to whatever is left over here, okay? So the mass flow rate of water times the water's enthalpy plus the mass flow rate of the air, 2 times enthalpy at stage 2 is equal to the mass flow rate at 0.3 times the enthalpy at 0.3. Okay? Usually in your questions, it's going to say that, oh, there's saturated water that enters over here, okay? So you could easily find the enthalpy of that water. Next, to find the mass flow rate of the water, you have to consider that omega is equal to the mass flow rate of water divided by mass flow rate of the air. Okay? Or vapor, sorry. Here. It's exactly the same thing. So, we know that mass flow rate of water is equal to omega times mass flow rate of the air. So, substituting that, you get ma times omega. This omega is different. I'll explain in a second. Plus m2 times h2 equals m3 h3. For problems like this, you have to consider that the mass flow rate of air stays the same at all points. A3, okay? So we could substitute this part out. And this over here, to find the omega over here, it's basically the water that's being introduced into the air. How do you find that? You just find the difference. This is in regards of the dry air, okay? So when you do the difference, it's basically what amount of water is being added. HW plus H2 equals H3. And that's your second rule for this type of problem. Next, for this type of problem, cooling and dehumidifier, again, there's step 1 over here. It goes through the cooling, step 2. So water is being removed, okay? So first rule is that omega 1 is not equal to omega 2. And second, in problems like this, it's going to give you a temperature of water that's exiting the system, okay? This water is generally considered saturated water. All right? And for these types of problem, you have to check the dew point temperature, okay? When you go to step 1, you check the dew point temperature. And if your temperature of the water is below the dew point temperature, then phi 2, the relative humidity is equal to 100%. All right, that's your second rule, and that's it for this problem. The rest is like exactly the same as last time. It's super easy. Next, evaporator cooling. This is probably like the easiest, okay? You have step 1, step 2. You have T1, phi 1, okay? With these values, you have to find the wet bulb temperature on your psychometric chart. It's going to be written something like this, okay? The rule is that this value stays the same at both points. And that's it. And also, omega 1 is different from omega 2. That's it. This is like probably the easiest problem. All right. Lastly, adiabatic mixing. This is probably the most complicated or complex, but it's like super easy. Don't worry. You're going to get 2 air streams, and they're going to combine into a third airstream. Okay? The first rule is the mass flow rate of the first airstream plus the mass flow rate of the second airstream, is equal to the mass flow rate of the third airstream. Okay? This is your first rule. Second, you have to take into account this principle. E in equals E out. So keep in mind that omega is equal to the mass flow rate of water divided by mass flow rate of the air. So mass flow rate of water is equal to omega times mass flow rate of air. All right. So mass flow rate of water at 0.3 times omega 3 is equal to mass flow rate of water at 0.2 times omega 2 plus mw1 times omega 1. Okay. We're going to replace mw with the omega ma. Okay. Omega 3 times ma3 equals omega 2 ma2 plus omega 1 ma1. That's your second rule. Your third rule is this exact same principle. ma1 times the enthalpy plus Ma2 times the enthalpy is equal to the final enthalpy. That's it. That's your third rule for this problem. Super easy. All right, let's do this heat and humidification problem just so we can understand better. Whatever the question is asking, I highlighted in yellow. So it's asking for us the heat that's being applied, the temperature and relative humidity at 0.2, and the mass flow rate of water, all right? So this is what we're given in the question, okay? Since you have two pieces of information, you can use the psychometric chart to find everything else, okay? So 10 degrees, using 10 degrees Celsius and 70% relative humidity. And we're going to read the psychometric chart to get these values over here. Okay. Since going from stage 1 to stage 2 is just heating, the water content stays the same. So omega 1 is equal to omega 2. Next, we can do the same thing for 0.3, okay? Using T3 as 20 degrees Celsius, phi 3 as 60%. We can read the psychometric chart to find all the values we need. All right. Now that you have this point, we're going to consider that going from stage 2 to stage 3, there's just water that's being added, okay? So no heat is being removed or added, okay? So the energy at 0.2 equals energy at 0.3. Mass flow rate of water times the enthalpy of water plus mass flow rate at 0.2 times enthalpy at 0.2 is equal to the final mass flow rate times enthalpy, the final enthalpy, okay? You have to keep in mind that omega is equal to m water divided by ma. And if you derive both, it's still going to be the same. It's still going to be equal to omega. Okay? Therefore, the mass flow rate of water is equal to omega times the mass flow rate of the dry air. Okay? Since the air content does not really change, this is just dry air, we know that Ma1 equal to Ma is equal to Ma2 is equal to Ma3. Okay? The content, like the Ma is just the dry air. It's not the water. Even the water is being added, the mass flow rate of dry air is the same. That never changed. So, we're going to consider over here, Mw is equal to Ma. I'm just going to write Ma because it's the same. Times omega times enthalpy plus Ma times H2 equals Ma times H3. We're going to divide Ma by everywhere. Next, for this omega over here, you can't just say, oh, it's omega 1 or omega 2. No, this omega over here, since we're dealing with water, it's the amount of water that's being added. The way you find that is you just have to do the difference of omega 3 negative omega 2. To find the enthalpy of water, it's over here. We have it right over here. It's saturated water at 100 degrees Celsius. So you just check your tables and you copy down the enthalpy and that's it. Plus H2 equals to H3. All right. So plugging in all the values, 0.0877 negative 5343. Enthalpy of water is 2675.6, reading the tables, plus, we don't know H2, is equal to 42.4. Solving for H2, we get H2 of about 33.2. We also have omega 2, which is equal to omega 1, 0.005343. Using these two values, you can use the psychometric chart to find all the values you need. So we can find T2 to be 19.6 degrees Celsius, and relative humidity is equal to 37.6%. That's our first answer. Next, to find the heat being added is just equal to the mass flow rate times delta H, okay? This is, you know this from your cycle problems, okay? So, the question already gives us the volumetric flow rate over here, 35 meters squared per second. So, you have to take into consideration that mass flow rate is equal to the volumetric flow rate divided by the specific volume, okay? So 35, this said the 35 meters squared per minute. So we're going to divide that by 60 to find the seconds. Divided by the specific volume at 0.1, because that's what we're given. Whoops, it's 9. This times the difference in enthalpy, 33.2 negative 23.5. We're taking H2 negative H1 because that's where the heating occurs, okay? This is going to give us a value of about 7 kilowatts. So that's our Q. Lastly, to find MW, we already know that it's equal to omega times MA. And omega is just the water being added. So you do the same thing again, 0.00877 negative 0.005343 times MA. You do the same thing over here, 0.809, and that's going to give you a volumetric flow rate, not a mass flow rate of 0.00247 kilograms of water per second. And that's how you solve these problems. All right, let's do one last example just because this problem is low-key kind of complicated. It's basically an adiabatic mixture, and the question is asking us to find the final conditions, okay? So, first of all, checking the first airflow over here, you have 32 degrees Celsius and 40% relative humidity. Basically, since we have two information, we can read the psychometric chart and find everything we need. To find the mass flow rate, we can use the volumetric flow rate divided by the specific volume. So 20 divided by 0.881, which is equal to about 0.378. Okay? Using the same principle for the second airstream, you have 12 degrees Celsius, 90%. Reading the psychometric chart, we get an omega of 0.007878. Enthalpy of about 31.943, and specific volume of about 0.818. Again, the mass flow rate is equal to the volumetric flow rate, 22, divided by the specific volume, 0.818, which is equal to about 0.51 kilograms per second. So we can find our first information. MA3 is equal to a combination of the two airstreams plus MA2 equal to 0.378 plus 0.51 equal to 0.888. This is MA3. Next, keep in mind that the water that's coming from both streams is equal to the combination of these two waters. It's just, adding up. So MW1 plus MW2 equals to MW3. Oh yeah. All right. So, whoops. Okay. Keep in mind that omega is equal to the mass of water divided by the mass of air. And if you derive those, it's still going to be the same ratio, okay? Therefore, the mass of water is equal to the mass flow rate times omega. Putting that into consideration, omega 3 times mass flow rate of 3 of dry air is equal to the combination of both plus omega 2 MA2. All right. We have everything. We can use all of this to find omega 3 is equal to omega 1. Well, I'm just going to copy down, okay? But you have all the information over here from the psychometric chart. 0.378 times 0.011956 plus 0.51 times 0.007878 divided by 0.888, giving us omega 3 to be equal to 0.0096 kilograms of water per kilograms of air. All right. Next. We know that there's no energy being exchanged or lost when these two streams are combining, okay? So, we know that the energy from the first stream plus the energy of the second stream is equal to the combination of both. We have all of these values except for H3, okay? So solving for H3, it's equal to M1H1 plus M2H2 divided by M3. All right? So plugging in all the values, I'm not going to copy everything down, but we get an H3 to be about 45.1. That's your enthalpy. So again, now that we have our enthalpy, 5.1, and our omega, 0.0096, we can read the psychometric chart to read the following, to read the final values, okay? So we get the dry bulb temperature to be 20.6 and relative volume to be 63.2%. That's it. Super easy. Like almost all of these problems, you just have to know how to read the psychometric chart. You get two of the values. You incorporate this principle, E in equals E out. And the rest is super easy. You just have to understand what you're doing. And that's it.